So what I want to do next is bring ERIC Martindale up to talk. ERIC has been building the technology for Portal in a way that has blown my freaking mind. And ERIC is going to be explaining the technology to you. Let me...
Totally, man. These are the best MacBooks ever made. Sorry, but they have a physical wired Ethernet, so I don't have to trust on all these stupid broken wireless technology. Or is it Nickelback these days? Is that what kids listen to? I heard that got taken down off of Twitter, actually. Copyright violation by the president. Precisely. I mean, it's a small enough section. Where's our lawyers in the room, right? Okay. Hopefully this comes through okay. Since we're just jumping into it, I'm just going to talk a little bit, just very briefly, just because I think it provides a little bit of context as to how I got here. My name's ERIC Martindale. I've been working in this space for a long time, but primarily when I read the Bitcoin white paper was on the cryptography mailing list. And like most young kids in 2008, probably not well-versed enough to fully understand the scope of what I was reading. The people themselves. And that really gave me a second thought about what Bitcoin was, what the context was, what it provided. And I started to dig a little bit more into the background of digital cash. I'd been pretty involved in virtual currencies up until this point, but mostly in the video game realm, right? I'd seen World of Warcraft Gold, I'd seen all these other things, but it didn't contextualize for me until I'd really had the political and economic context to start realizing exactly what money was. So in 2011, I became the crazy uncle. I think a lot of us can probably identify with this story, maybe not in the same dates, but my parents pretty much kicked me out of Thanksgiving dinner one year just because the only thing I wanted to talk about was how Bitcoin was going to save the world from these damned central banking, the institution of central banking. Well, 2 years later, I've been continuing to go parrot the same idea back to the businesses there in town and try to convince them to accept this newfound currency. Hey guys, Bitcoin is really the way out of this. Like, you can bypass all these government fees and you can, keep a little bit more of the money for yourself. And I was telling everybody at the time, and so I caught the attention of BitPay, which some of you may be familiar with. So at BitPay at the time, it was a very unique market. Bitcoin was just barely coming onto people's radar. I don't even think there was college classes about it yet. They were starting to come out. They started to come out in 2014, 15, I think, was some of the first ones. But BitPay was, focused on consumer and merchant adoption of Bitcoin as a currency. So this really gave me context and meaning to a lot of the future engineering work that I did. We worked on a lot of open source stuff back then. It was a lot easier to commit engineering resources to open source things when you're such a brand new fledgling company and you find yourself raising millions and millions of dollars from VCs who are ready to throw money at what could be a hedge against global financial collapse. So they wanted to be there. So we built something called ChainDB, which is one of the first sidechain implementations. We built Impulse, which was actually one of the first payment channel networks. You can think of this like Lightning, kind of just very early before Lightning was even formalized. And we also worked on Foxtrot. These were all open source things. I think I got the opportunity to release ChainDB at MIT. Impulse was released at the same time, and then Foxtrot, I don't know that they ever actually open sourced, unfortunately. But you'll find this is kind of a trend, especially recently, where you have a business case and then you have open source work that a company might rely on. Unfortunately, you find it very difficult to justify contributing to code that other people can use if it seems like that's your core business. But that's not what Bitcoin is, right? But just to fast forward a little bit, in 2015, I decided to part ways from BitPay, seeing the door on open source funding starting to close up. And starting to see the opportunity that Blockstream presented, which was some of the original Bitcoin Core developers decided to raise some funding and come together and work on some of these other really good ideas like sidechains. So the place where we had seen the sidechains paper was actually from this group here, so I had the opportunity to work with them. We worked on a project called Elements, which is a fork of the Bitcoin code base, which implements things called confidential transactions. So this is a way of using range proofs and a couple of other really clever cryptographic tricks to do confidential transactions where you cannot see the value of a particular transaction. So if I'm transferring 10 BTC to you, you actually cannot see, or nobody else on the network other than you can see that you're transferring that 10 BTC. We also tested and implemented segregated witness there, a couple of new opcodes which can be useful for a number of things which I'll get into later. Holds a key and manages a signer or block generator inside of a group. But this is the first commercial application. But just like BitPay, we weren't really seeing adoption. Right? We're seeing this blockchain hype, we're seeing this super big surge in attention towards the technology, but then we're not really seeing this end user consumer facing application, right? We're not seeing user facing applications that are directly using Bitcoin. So that gave me a lot of pause and a lot of thought about this stuff. So I officially started Fabric Labs to kind of attempt to solve this problem coming out of Blockstream in 2017. You can kind of look at where my thinking was at the time. There's a pretty good Coinbase article describing this. But this is a trend for me. I've always been interested in working on distributed and properly decentralized systems. And this just kind of colors the work that I'm about to present. But Fabric Labs, I want to point out, I took a hiatus between BitPay and Blockstream in the summer of 2015. When I went to Hyperledger for the very first time at Blockstream's behest, there was a big conversation in the room. It's, how are we going to build a blockchain for enterprise? And that just rubbed me the wrong way. In an exchange, for example, it makes a lot of sense to aggregate liquidity, aggregate these orders into a centralized place, because otherwise, how else can you be so certain that you're getting a fair price? If you don't have the full view into all of the available orders, right? You can't be certain that you have a fair price. So that's one thing here. Without going through a financial institution, so this really strikes back at sort of what ultimately drove me to Bitcoin, which is this true financial revolution. I really do, I said this then and I still continue to say now that Bitcoin represents the greatest wealth transfer in human history. And we've got time. We're still super early. Bitcoin, if you look at the protocol itself, is not really scheduled to be completely distributed until, according to the mining schedule, the year 2140. Okay, so I personally view Bitcoin as sort of this huge transition for how civilization is organized, and I'll save that for the panel and the discussion afterwards. But I really wanted to hit on this just because it's the original source material. Obviously, this is where you can find it if you still need it. Pretty easy to remember. But where are we today? This is one of my favorite graphics just because it kind of captures everything for me. There's a saying in engineering, well, especially when you look at internet engineering and the web and all the technologies, the amazing things that we've done over the past 20 or 30 years. But it's all crumbling at the very foundations, right? We moved very quickly. We deployed a lot of really powerful systems before certain things were even available, right? So we barely even had RSA in the beginnings of the World Wide Web, let alone now knowing that RSA is continuing to crack and be broken, let alone DSA and many of the other cryptographic techniques that we needed to keep things private, right? And you start to see the outcome of what happens when you build a whole house of cards up so quickly and you allow an entire ecosystem to kind of just lump on top without ever addressing those core underlying issues. And I think Bitcoin represents a potential way out. And I'll get to that in a minute. So just for those of you who aren't aware, I'll get through this quickly, really clear technicals. These are how Bitcoin transactions work. Each contract is basically encoded here inside of this where it says public key. If you can validate against that contract, if you can validate against the script, if you can validate a 1 or a true in this contract saying that, yes, I have the correct corresponding private key to this public key, I'm generating a signature, and that is what creates an output which can then be spent in a future transaction. This doesn't have to be just a public key, right? This can be any number of other script operands, script being the language that Bitcoin uses for its contract validation. But there's a lot of other really powerful things that we can do with this if we can control and call this a smart contract for just a single key, well, we can also call it a smart contract for multiple keys. We can also write programs in this space. But one thing that we have to remember is that every time we broadcast a transaction that is going to be included on the main chain, that's a transaction that's going into an immutable record of history for all time. And if you want to start talking about unstoppable trade and fair exchange and censorship-resistant anything, having a public record of your transactions is a liability, not an asset, right? It's because anybody can then go back and keep track and take a look at where the money is flowing, who has access to it, and that becomes your prime candidates for other forms of oppression, which can be viewed as censorship. And also on the network level, you can see the stuff at the network level, so you have to be aware of that. So I started thinking about, well, how do you fix that? Well, first, before I get into how do you fix it, let me show you some of the other powerful stuff that you can do. This is a traditional Bitcoin pay-to-public key hash. This is the, if you think back to very, very early computer science days, assembly, right? We're writing these very simple instructions that the computer is reading from top to bottom. We're not writing very human-friendly contracts at this point, but we'll get to that in a minute. But there's signature, which should be on top of that, and then that validates that the transaction is valid. This is how up-to-date traditional Bitcoin transactions work, but there's more that we can do. All we do to spend this is we concatenate our signature to the top of that, and then that is considered one transaction. This is encoded as hex, actually. It's got a couple of other pieces in the actual transaction data that I'll get into in a minute. But that's how you spend it. Just you pass the signature in, you concatenate it, and then that is a valid transaction to the rest of the network. But what else? Well, let's look at multisig. And I've gone ahead and put a little bit of description here on the right-hand side just to kind of describe what it is, so I'm not just reading it out to you. But Bitcoin has a built-in multisig, a multisig opcode, which is what's called a 2 of 2 multisig, right? So a 2 of 2 multisig, we only have Alice and Bob as the public keys, so maybe this is me and you, right? I'm going to say that there are going to be 2 signatures in the set, and then I'm going to require both signatures, so we both have to agree. We both have to agree on what the terms of this contract are in order for us to spend it. So that means that if I create the first version of this transaction and I pass you a partial signature, something I'm not going to cover today, then it's not going to be considered valid until also you add your signature, right? So Alice and Bob both have to combine their signatures for this money to be spendable by those people. This is just a very simple concept of multisig. Okay? So think about these as tools in a toolbox that you can use to construct much larger systems. Well, what else can we do? Well, this is the killer one, I think, and it's a little bit more complicated. But just like before, I went ahead and wrote out the human language version for the lawyers in the room. Basically, what we're doing is we're checking to see if some input, when hashed by SHA-256, which is a hash function, a one-way trapdoor function, if the hash is if they're able to provide some secret which matches this hash, right? So we knew the secret in advance when we constructed this transaction. But if somebody else gets it, then and it equals, then they can spend it. Okay, right? So this is what's called a hash lock in Bitcoin, and this is really the foundation of most modern Bitcoin smart contracting. Okay, now there's the else case, which is kind of the failover case. This uses a special opcode called opcheck sequence verify, which basically can check one of 2 things. It can either check the number of blocks since this transaction was confirmed, or it can check the number of clock seconds since the transaction was confirmed. Right? So what this allows us to do is say if we have a counterparty, I will let them spend the funds, but only when they have this secret. And then there's a timeout. So this is the lock time, and then I can redeem the funds back to myself. So this is a live on-chain transaction that's secured by Bitcoin's thermodynamic security. So we can offer up, as long as we know our counterparty, we can offer up some funds in exchange for some other piece of information. This is the same construction that's used in what's known as the original Tier-Nolan swap. Tier-Nolan swaps are what are called a mechanism of atomic cross-chain swaps. So if I have another chain that operates in the same way, say Litecoin, for example, they've already done this between Litecoin and Bitcoin, I can go spend some funds revealing this hash on the Litecoin chain, right? In order to spend those funds, I have to reveal the hash, because if we remember back before, you had to concatenate some data, right? You had to provide the input script. This is what's called the redeem script. And in spending that Litecoin, I will reveal the secret, so that my counterparty will then now have the secret. Everybody else has the secret too, but they don't have the public key, the same public key, right? But everybody now sees that secret. It's now a valid transaction, and now. But the thing we want to actually look at is the SIG hash mode. So this field is typically what's used in a standard Bitcoin transaction, right? It's what allows us to define what in the transaction the signature is going to cover. Okay. So in a traditional Bitcoin transaction, we use SIG hash all, right? It means that all of the inputs and all of the outputs are going to be covered by the signature. So using my cryptographic key, take the hash of the signature, I sign that, that's my signature, and then that proves it. But, before I get to payment channels actually, but there are a couple of other SIG hash modes, including SIG hash none, where none of the inputs are covered, SIG hash single, where only one of the inputs are covered, and SIG hash anyone can pay, and I'll get into that here in a minute. This is slightly out of order, but I may as well cover this. So I was talking about payment channels. So a simple construction of a payment channel might be using one of those 2 of 2 multisigs, where if we want to say, maybe I'm paying you for internet, right? I just moved in, and I don't have my internet set up at my house. So I walk over and knock on your door, and I say, I will pay you per kilobyte of data that I stream across your Wi-Fi, right? And because we're both clever Bitcoiners, we already have the ability to construct a special set of transactions between one another, where every time my computer consumes a byte from your Wi-Fi, or every time your Wi-Fi sees my computer spending a byte, it creates a new transaction, right? And it does a partial signature of that transaction, and it passes that transaction over to me. Now, theoretically, I can construct the same exact transaction, provided we have a good signature aggregation scheme, or if I partially sign Bitcoin transactions, which is another thing that's coming down the pipeline. But provided that we both agree and we establish this contract, we can both anchor into the blockchain and then have a channel between us where I create a new transaction every kilobyte. Or maybe it's even every byte if my CPU is fast enough, right? And I'm just handing you authorization of me paying you out of this existing balance that exists in one transaction output on the chain, and I'm paying you per byte of data or per kilobyte of data. This is a good example of what a payment channel would be useful for. We use the same construction a little bit later on when I show you a little bit more about this. But this is what allows on a single core. It seems like, and this is some pretty fast hardware. I didn't put the full stats on here, but we're exceeding about 2,000 signatures per second on some of the latest hardware that's available. So you start thinking about when Bitcoin is for everybody, and a lot of the engineering perspective of Bitcoin is go slow, take it easy, and make it as accessible for everybody as possible, right? The lowest end devices should be able to run Bitcoin. Otherwise, the people at the lowest end of the scale are not going to have access to Bitcoin, because they will have to rely on trusted services to run their Bitcoin stuff, right? And what is Bitcoin but a trusted system, a peer-to-peer system that does not rely on trusted third parties, right? So if you're relying on trusted third parties, you're really not using Bitcoin. But we think pretty much, between peers, and again, this is not a flood network, so this doesn't have to be broadcast out to the whole network, right? This is just peer-to-peer, so this can scale, pretty widely. I don't really see. I'm sure there are cases in the near future even that will exceed this on an individual basis, but not for really any kind of individual needs. And I think this is where Lightning kind of targets. Lightning targets small one-time payments, whereas a network that we're going to be going into, which is for compute, needs to be much faster. So this actually works out really well in our favor at the end of the day. Talked about wireless. This is really useful. Micropayments in general are extremely useful. One of the reasons that people don't, I guess people don't get into it anymore, but PayPal charges, if you want to set up a micropayment system inside of your app, PayPal's license fees are in the order of like 15 cents per transaction, right? So if you start talking about payments that are less than 10 cents for like a small little in-game item or something like that, you really can't use PayPal for these services just because of the overhead and because of the fees that they put on top. And it kind of sucks. But it turns out we can use Bitcoin and we can use these underlying technologies. I'm really excited about incentivized mesh networking, so using payment channels for individual nodes to share data bandwidth, basically. So be able to connect to a node and say, I'm going to pay X amount of satoshis per megabyte of data that I transmit, right? So then we have an actual contract that sits on the Bitcoin blockchain that allows me to pay you for that. Get into these signature hash modes really quickly, just because these are the building blocks. These are the fundamental building blocks that we use. SigHash single I talked about already. So it allows you to only cover one input with your signature, so I can broadcast a transaction that's spendable in the future when other inputs are provided. But it's not valid until it has those inputs. So the sum of the outputs has to equal the inputs for it to be valid on the network. So we can use some off-chain protocols to exchange those signatures and then later broadcast a valid Bitcoin transaction. SigHash anyone can pay. I didn't really felt like I needed to put any details on this one, but SigHash anyone can pay basically allows anybody to provide the inputs in the same way that SigHash single does, but it allows you to use any of the inputs. So basically, if I have a transaction, I'd like to create a spendable output to my key for 10 Bitcoin, and then I put together some social media campaign, like I'm raising money for X, Y, or Z, right? I can broadcast that, and then provided people's wallets support it, which that's a drawback of today, is a lot of wallets don't support these complex types of transactions. They can fill this in, and it will become a valid transaction when it meets that threshold, but no sooner, right? So I can basically do a crowdfunding campaign directly on top of Bitcoin and have it cryptographically enforced without having to use any trusted third parties. SigHash no input. This is one that is not in Bitcoin as of yet, but there is a very heated discussion taking place right now as to whether or not it's going to get in. And I trailed off here when I was adding it because it really is such a big beast. But it allows me to sign a transaction without covering any of the inputs in the same way that SigHash anyone can pay can do, but I can control the outputs, right? So I can write code in my script which determines where exactly a particular chunk of that payment will go, under what conditions, using the same smart contracting abilities that I was highlighting earlier. So we can lock these up in the multi-sig contracts. So these can be payment channels. They can be longer hash locks or time locks. But SigHash no input, really powerful. Keep your eye on it and read the debate. Read the debate. I think that'll give you some good context. Let's see. So nobody really likes writing this this crazy assembly-looking language, right? It's not really familiar. We're really familiar to having compilers handle our loop unrolling for us. Tail call optimizations in modern programming make pretty much all programming reasonably well efficient. So we don't have to really think about that. But there's a new project by Peter Wool and others, I should point. There's a lot of efforts in this direction, but it seems like Miniscript is going to be where it heads up. So Miniscript is I'll call it Lisp-like, but it's an additive language it's composable in the sense that you can write these little conditions, right? So has these two signatures and these other two signatures, right? And so you can start creating really much more complex logic with signature groups, much more complex logic than what you might want to have to do in script, because it can be a little bit unwieldy. I don't have any examples of it up right now, but you can go read Peter Wool's BIP, Bitcoin Improvement Proposal. I think that'll cover some ground. Taproot and Graftroot are also kind of in the same realm of what we're working on. So Taproot and Graftroot use what's called a tweaked public key. So if I have some secret, I can tweak my public key using that secret, and anybody who sees it doesn't necessarily know that the public key has been tweaked, but can infer some information out of the resulting data because they also know the secret. Okay, now this is an area of debate and research right now as to which direction it's going to go, which implementation it's going to take, et cetera, but this is an area for future research that I think that will be very powerful for Bitcoin smart contracting in the near future, provided it doesn't go through another hullabaloo in getting it merged. But we'll talk about that in a minute. I'm actually seeing it on screen. Merkleized abstract syntax trees. So this is something that's been talked about in Bitcoin land for a long time, but it has only recently gotten to the point where certain components of Bitcoin may adopt this. And a Merkleized abstract syntax tree, for lack of a better phrase, is, well, it's a representation of a program. It's a syntax tree where each step in the program is included in a Merkle tree, right? So each branch in a program has a branch in the Merkle tree, and I can, by computing that program, whatever path that my computation falls down, I will be able to prove that I executed that computation by sharing the element in the Merkle tree upon which my result landed, right? So this is what's called a Merkleized abstract syntax tree. This has a number of benefits, not the least of which that I'm most excited about are performance, or privacy. That's the one I'm most excited about. But I think maybe Peter would say that he's most excited about the space and performance optimizations. So rather than sharing your whole program on chain, right? Instead of sharing your whole contract on chain, maybe you only share the pathway that executed. So Bitcoin multisig today, if you broadcast it on chain, you not only reveal which parties in your multi-signature set signed the transaction, but you also reveal the parties that didn't sign, right? So it's a very serious concern, especially for, say, a corporate board which might want to manage its finances on chain. Well, they would be revealing a lot of information, and that's just unacceptable from a privacy standpoint. Whereas Merkleized abstract syntax trees, since we're writing to a database that's going to be around for 10,000 years, right? We want to write the minimal amount of information possible, right? So this is something that's super powerful for writing smart contracts down at the base layer. This is my conclusion. Really technical, I guess, but just kind of giving you the runaround on all of the different pieces that we can build things with. They're powerful, but they're also dangerous because, I don't know if you saw my hat, it says make Ethereum immutable. But Bitcoin is irreversible, at least as far as we've seen, and that's kind of the value that it provides, is it provides an immutable record of account. We'd refer to this as a base layer because we can build what's called a sound money using this immutable record of account, but it also means that we have to be very thoughtful about how we move and spend this money because, again, there's a fixed amount of space in the chain, right? And there's what could be a pretty almost unlimited upside on the demand for space in that chain. If you start thinking about records of every single interaction that we might want to keep, we obviously don't want to keep the entire video record, right? But we may want to keep some receipt that piece of data exists at some point in time. And if it's valuable enough based on the current Bitcoin transaction fees, then maybe Bitcoin makes sense for you, especially if you want your data to be around for 10,000 years. So what is this layer 2 thing, and why do people get crazy when you start talking about layers? Well, what is layer 2 to me? I just kind of quickly wrote out, and there's a compelling alternative to it in Ethereum land. I believe Raiden is probably the closest related to Lightning. Again, I stay fairly in my lane when it comes to Bitcoin. I'm an engineer, so it's pretty difficult, but I will avoid lambasting the engineering decisions of others. But I really do. I really think that Bitcoin has superior properties in a lot of ways. So that's what I've been focused on. Rootstock is another great one. So Rootstock is a side chain. Rootstock is another. Currently, it's got some combination of federated plus merge mined. I don't know if anybody's paid too much attention to it, but it is a side chain where Lightning is a mesh network of sorts, where individual peers can connect to one another and send messages to one another and make smaller payments across these payment channels. Rootstock is a completely separate chain. But when I say merge mined, it means that the miners on Bitcoin are also competing at the same time for the blocks on tracks. It uses the EVM. So Rootstock is another great example of a layer 2 network where I can move Bitcoin from layer 1 into layer 2, can now run contracts as if it was Ethereum, can move my Bitcoin around, can run anything Ethereum or the EVM can do, and then later withdraw my Bitcoin back down to the main chain. Okay? But what about this layer 3 stuff? Okay? And I don't have my animation here, but I want you to just kind of work with me on imagining for a second. So if we have a network at layer 2 of these payment channels, right? These nodes that are communicating between one another, and they're able to make very, very small, fast payments between one another. Okay? We can construct a graph of transactions that are only shared with some portion of that network, and a portion of that graph is only shared with the other portion of that network. By selectively revealing these secrets, we can define a path in the tree which is most likely to be executed at layer 1. Right? So we're going to be building up a directed graph of potential energy that is based on the energy in each individual payment channel. Okay? Now using this, we can do something called a secure multi-party computation. This relies on something called a zero-knowledge contingent payment, or a ZKCP in short. But the secure multi-party computation is a way of dividing some provable computation into smaller subsegments, distributing it out across the network, and then having those parties complete multiple rounds of computation where they pass an encrypted blob off to the next person, off to the next person, off to the next person, and each hop applies some new transformation to that encrypted blob. Because they're responsible for executing a portion of the computation, they have to actually perform that version of the computation in order for the result of their computation to be valid as per the prover program. People get really excited about this in ZK Stark land, in ZK Snark land. All of the non-interactive zero-knowledge proofs are exactly the direction that we're going here. And there are multiple different constructions. But here's the basics of it. I do want to say that this has been a field that has received a lot of advancement in the past 5 to 10 years, whereas this was mostly theoretical and really just toy implementation from the early 90s through the 2000s. Yao et al. Actually ended up coming up with this thing called garbled circuits. I won't get into the paper, but I think it was originally 2011 that he published that paper. So that's kind of the holy grail there. But by basically, rather than writing it as a program that compiles down to, just like assembly, for example, which gets executed on your CPU, what we want to do is we want to break it into Boolean gates or logical arithmetic gates, right? So the transformation that each hop takes is just a pure mathematical transformation on some piece of data that they can't really see. Now again, this is a super high level overview, but please read the papers, really incredible stuff. But what this allows us to do is allows us to encrypt a piece of information, distribute some program, and then when we distribute that information, we can encrypt it in such a way that the program can run on top of it, such that nobody who's in that nobody's participating in running that program can see the data they're running it on, but they can prove to anybody on the outside that they have computed it correctly, right? So this is really the crucial part here. So what can we build? So this here is just a really quick overview. I think this will play, maybe? No. Video cannot be loaded. Well, what we had here was a lovely animated graph representation of the different gates in a high-level contract. So each... That's probably, yeah, I'm air-gapped, not it. I'm sure we'll be sharing it out afterwards. But basically, what you're seeing here, or what you will see here if it loads, is each successive step of our program. So this is a contract that's executing live. Each one of these hops is a MPC contract. So there are multiple steps in the program that we're creating, and I'll get to the UI here in a second. I really wish it would connect. Give me 1 second here. Okay, yeah, so what you're watching here is the program progressing through a multi-party contract. So some of this stuff is going to look relatively familiar to you as like probably a developer-oriented at least. So we're calling a couple methods. Here in this case, we're going to add a couple depositors. In this case, we're going to be reading some input from the terminal. So there are certain types of programs that are not easily modeled in this way. So we have a sort of a stopgap, like user input and output is one of those things. The program needs to halt to wait for user input, typically. Now you can have other because we're separating things out, you can actually have separate, did it stop here? Yeah, it's a bummer. All right, that's just not going to work. But each one of these hops, there's a payment channel taking place between the parties that are participating in each step. And each party validates it, otherwise they stand to lose some portion of their security deposit. So you can think about this like proof of stake, except we're not issuing our own currency. And I don't think that, personally, I don't think that issuing your own currency and then also securing that currency through proof of stake is a wise decision. But I won't get into that too much as of right now. We'll get to Q&A in a bit. Bummer. Let's move on to the next one. So just to kind of jump into it, the product, I ended up partnering up with Chandra and George here at Portal to build Portal, which is what we call Unstoppable Exchange. So using this construction, this SMPC construction, where multiple parties are earning small slices of Bitcoin payments in exchange for proving the computation that they computed this order book, Portal is the downstream product that we've ended up constructing, and this is a consumer-facing product. Let's hope that this one works. Let's see here. So this is going to be Alice and Bob. This is what a user interface looks like. Bitcoin development doesn't have to be slow and chunky, right? As once you get these core layer 2 pieces done, once you get these transactions, once you get it so that you can divide up computations and make very small payments in exchange for these computations, you can build a pretty nice and reasonable UI. And again, unfortunately, it's not seeming to load too quickly here. But you can see it here on the left hand.
Work better than the video.
That's right. Okay, so basically what would happen here is we've got Alice and Bob. Bob is going to lock up some Bitcoin in one of these HTLC swaps. Similarly, on the Ethereum side, they're going to be able to see that this trade was created, that the Bitcoin was locked up, and then they can lay claim to that, and that transaction fills out the opposite side of the transaction on Bitcoin side. It reveals the secret on Ethereum side when Bob claims his Bitcoin from Alice, unlocking the Bitcoin on the other side, which I showed you there. I just wish this would progress. Unfortunately, it is dying. Let's see. Okay, so since the videos aren't working great, we'll just kind of give you an overview here. So this is the overview of layer 2 and layer 3. You can look at Lightning again like a layer 2 solution where you're bonding into a base layer chain at layer 1. You're exchanging small payments with one another but not broadcasting them on chain until you absolutely need to settle. But layer 3 is much more of a network where you have an entire tree of potential transactions, and the only way that you can know which one of these transactions or which one is actually a valid transaction is by reading through them and matching them in your order book. So this is the ZK circuit here. Basically, the order book is written as a zero-knowledge program distributed as a contract, so transactions can be signed into the order book. The order book is not visible to the parties unless you actually have an order in the order book, at which point you have an awareness of what position your order is in the order book. But the executors can then lay claim to a small payment for correctly proving that they've sorted the order book and proving that, that two transactions on either side were both included in some, what we call an anonymity set, because you can basically think about this as like a giant incentivized mixer, right? So because everything is going into a zero-knowledge black box, there is a zero-knowledge sort taking place. What comes out outside of the black box is basically filled orders. Nobody saw what everybody else's order was. Nobody knows what the actual pricing information is other than the execution of their own orders. And basically the only transactions, the only information that leaks is the information that eventually, potentially, settles back down to the main chain. Now, because this is layer 3, we can keep those transactions separate in private components of layer 2. And this is really the reason that we keep things isolated out, is we want all of the, because blockchains in general are very difficult to achieve privacy with. You know, we talked about some of these questions about whether or not, you know, what if a Bitcoin transaction would reveal, you know, some personally identifying information? Well, it does, right? If you broadcast a Bitcoin transaction, you're revealing your IP address if you're not using Tor, which how many of you connect to Tor on your phone when you're going to go buy, you know, a coffee with your Bitcoin, right? Not very many of you. So basically what we're doing is we're trying to separate things out into isolated concerns, right? We don't need the entire Bitcoin mining network to be computing our individual tiny little trades, right? What we want is we want a targeted set of competitive users competing for that type of computation, and we want to be able to pay them for it, but we also want to be able to prove that they have executed those computations correctly. So we basically use layer 2 as a computational substrate, if you will, for revealing branches in the tree that are valid. And then we use that to construct really a von Neumann machine, so a proper computational environment as a ZK system on top of layer 2. So that's our approach. Portal, I think Chandra may want to give a quick where we can get the URLs and all of that stuff. But I think I got it up here, so I guess we'll just roll into Q&A. So that's it. We have most of it working, not the ZK circuit decompilation or circuit compilation components. There is an open source library actually out of Stanford that we're using extensively right now. We have all the layer 2 elements basically built out. So that's what we've built out for these guys. We've probably got another 2 months on the ZK components of it. So yeah.
Any other questions?
Questions?
Before we move on to the panel?
Does it use all of those layer 2 solutions in like parallel, or is that theoretical?
We have our own layer 2 network, right? So we can receive deposits from Lightning just because they're normal Bitcoin transactions. Rootstock is a completely separate system. We can connect to it. We haven't written too many integrations. The HTLC tree is meant to describe our stuff. Raiden we haven't really interacted with, but any layer 2 system on top of Bitcoin is going to be using a regular Bitcoin transaction. So if it has an output that's spendable, we can use that as a bond into our layer 2 system as well. So it should be just fine.
Does there need to be support on layer 1 for the order book to accept transactions?
No, and just back this stuff makes most of these special types of transactions indistinguishable from regular Bitcoin transactions. So that's an important aspect. Now we don't have that in use right now, so it's pretty obvious which transactions are ours. But yeah, that's future work.
So it can theoretically support any?
Yes, theoretically yes. Yeah.
This might be the coolest thing I've seen in a while.
Thank you.
Yeah, what's the usefulness of this in exchange for things that aren't exchanges between cryptos?
So.
Sorry, hard question, I know.
That's a fun question. This technique is applicable to pretty much all of modern compute. So any program that can be decomposed down to a polynomial program, which is almost all programs, We call this a finitary complete as opposed to Turing complete. So as long as you can define the space of your compute, you can write a proof about it. And if you can write a proof about it, then you can write a polynomial. And if you can write a polynomial, then you can divide it up into subcomponents and run it. So really, I mean, there is a general purpose compute application here, but any business that spreads itself too thin across too many domains and too many markets will not succeed, I don't think. Very rare cases. So really we're honing in and focusing on digital currency exchange specifically for this application. And there's no reason that the network, that the parties that are computing in that environment won't also compete for other types of computations, right? So I think that is a good question, actually.
Can you just give an example of one of those computations you trade?
I mean, personally, I'm excited about doing biological compute, scientific compute, right? If I have some way of saying like, hey, I need to subdivide up these computations, kind of like the folding at home kind of approach. That's more kind-hearted, I guess, out of my own goodwill rather than anything else. But yeah, anything that requires secure distributed compute. The secure compute aspect is really what's key here. If you have multiple parties that need access to something, I think selective disclosure is the phrase that's used, right? Where multiple parties are putting in data. The only data that they have rights to see is their own data, right? But they still need to compute some, like insurance data is another great example. Maybe the insurance company doesn't need to know your exact age. It doesn't need to know details of your medical records. But it has some function that it applies in the actuarial department to use that as inputs. But they don't need to know what the inputs are. They just need to compute some meaningful number on the other side of it. That's a good example, I would say, right there. But pretty much any environment where there's more than two parties and they need to have some sort of they're in an untrusted environment and they need to have some sort of way to prove some sort of secure computation. Yeah.
What's the advantage of using you over using secure enclaves, for example?
Well, trust assumptions, number one. Secure enclaves is a class. You're generally trusting the manufacturer as well as the supply line. So that's another deep concern. There are trade-offs with anything. What we're trying to do is not necessarily think about decentralization as a goal, right? Because decentralization is a property, right? It's a sliding scale. It's a measurement. What we're looking for is trust minimization, right? So how do we minimize the trust that's included in whatever arrangement or whatever construction that we're building? And in this case, there is a third party. They're just not a trusted third party in the sense that they're providing compute services, right? It's just not a trusted third party. So it doesn't really fall on the decentralization, centralization scale, but I think about it in terms of trust minimization. So.
What about cost and throughput, if they're related?
Yes, so this is approximately 20 to 30 times more expensive than traditional x86 general purpose compute. So you're at this scale, you're not likely to, at this scale you could probably compete with an Amazon EC2 just because I know that they have excessive margins, right? So if you're buying physical metal, you're going to get your costs really much cheaper and so on. But again, it's just like the trade-offs, right? Even though it's going to be much more, it's not much more, and this number is coming down. It came down from like 200 times down to like 100 times down to like 30 times. So I think we're doing good in terms of it being useful on mobile devices. That's the main question, is can mobile devices compete in the market? But I think it's basically limited to some degree by the number of signature operations that you can perform per second. So I think 2,000 is like an upper threshold for your setup in one case if you're not making any asynchrony assumptions. If you have parallel processing, you kind of got to lockstep with each branch in the graph and so on. So it's a little bit more difficult. But I think this is going to be fast enough based on the numbers we're seeing. This is going to be fast enough for regular consumer trade.
Transaction throughput was more what I was thinking, like with the exchange application.
Yeah.
Like how many?
So right now it's looking more like 200 to 300 per second is the upper threshold. But that's you'll notice is significantly below what a single payment channel might be capable of. That's because by definition you're splitting things up and you've got to kind of communicate with multiple parties. There's a number of rounds that you have to compute. So network latency plays into this a lot. There's so many variables in this that it's like until we really get more and more real transactions going through, we can run simulations, but real hardware is really going to be the real telltale. So.
Questions?
All right.
Thank you, Eric.
Cool. Thanks, man.